Assalamualaikum warahmatullahi wabarakatuh. So today we're going to continue on the chapter of AM modulation and demodulation. So last week I already discussed about the AM modulation. So this week we're going to discuss on the demodulation of amplitude AM. So we're going to look into the demodulation of DSBFC AM. So AM demodulation is the reverse process of AM modulation. A conventional double sideband AM receiver simply convert a received amplitude modulated wave back to the original source information. So to do this, a receiver must be capable of receiving, amplifying and demodulating an AM wave. It must also be capable of band limiting the total radio frequency spectrum to a specific desired band of frequency. So the selection process is called tuning the receiver. So we're going to look at the figure in the next slide of the simplified block diagram of a typical AM receiver. So this is the block diagram of the AM receiver. So if you look at this, from your left side is the antenna that will receive the AM signal, and after the antenna it goes to the amplifier, which will amplify the amplitude AM wave. So after that it goes to the mixer. So what mixer did is it will convert the AM wave which is the RF to the IF. So IF is the intermediate frequency, so it downscale the frequency to a lower frequency so that can be processed through the receiver. So after the mixer, it will go through IF amplifier. So amplifier will amplify the signal, the IF signal, and after that it will go to the detector. So detector is the demodulator. So from AM signal, it will convert, it will demodulate, and only after the wave go out, it will only receive the baseband signal, or what we call modulating signal. So, and after that, before it goes to the speaker, the signal, the baseband signal, will be amplified again to boost the signal. So we're going to look at the demodulator circuit. So this is the simplest demodulator circuit. We call it diode detector. Because why we call it diode? Because it uses diodes. So the diodes, the purpose of the diode is to rectify the signal. So from AM signal here on your left side, it will be, after it goes to the diode, it will be like at the middle figure here, signal. So it will rectify it, remove the negative side, and then the capacitor will remove the what we call unwanted RF, which is the carrier frequency. So the signal that goes out from the circuit will only be the baseband signal or the modulated signal over here. There are several parameters, receiver parameters, commonly used to evaluate the ability of receiver to successfully demodulate a radio signal. The most important parameters are selectivity and sensitivity, which are often used to compare the quality of one radio receiver to another. So first we're going to look into the selectivity. Selectivity is the ability of a receiver to accept a given band of frequency and reject all others. So using the bandwidth of receiver at the -3 dB point, we're going to compare it to another point which is at -60 dB. So the ratio of these two, we call it shape factor, SF. So SF is equal to bandwidth at the point of -60 dB divided by bandwidth at the point of -3 dB. So this figure shows how you can obtain the bandwidth at -3 dB and -60 dB. For example, you have a response like this, which is a frequency response. So you need to make a line at -3 dB and another one at -60 dB. So the point that cross the response, frequency response, will be the F1, the first point, and the second point, the last point, will be the F2. So to get the bandwidth is you just minus the F2 and F1. So bandwidth is equal to F2 minus F1. So similar at point -60 dB, where you have to if you need to get the bandwidth, you have to use this formula. So this at this point, F2 prime minus F1 prime to get the bandwidth. So another parameter that you need to know is the selectivity. Selectivity refers to the ability of a receiver to select a signal of a desired frequency while rejecting those on close adjacent frequency. So a receiver with good selectivity will isolate the desired signal in the RF spectrum and eliminate all other signals. So this can be obtained by using tuned circuit. So tuned circuit consists of L and C, inductor and capacitor. So the LC circuit tuned to resonate at the desired frequency. So the Q factor or quality factor of this tuned circuit determine the selectivity. So Q is the ratio of inductive reactance to resistance. So Q equal to XL over R. And also you can use another equation, which is the bandwidth is equal to F frequency, the desired frequency, divided by the Q or quality factor. Let's look into this example. For an AM commercial broadcast band receiver operating from 525 kHz to 1605 kHz with an input filter Q factor of 54, determine the bandwidth at the low and high end of the RF spectrum. So for this question, we're just going to use the formula of BW equal to F over Q. So in this question, you need to find the low and the high end of the RF spectrum. So bandwidth is equal to, at the lower band, we can use 540 kilohertz divide by 54 and we get 10 kilohertz bandwidth, while at the higher end we will get 1600K divided by 54 you will get 29630 kilohertz. So why we start at 540 rather than 535? Because the 5 kilohertz is used as the guide band of the AM frequency. So the minimal RF signal that can be detected at the input of a receiver still produce a usable demodulation input signal, also called receiver threshold. Depends on the noise power present at the input of the receiver, the receiver noise figure, sensitivity of AM detector, and the bandwidth improve factor of the receiver. The best way to improve sensitivity is by reducing the noise level, which we can reduce the temperature or reduce the bandwidth of the receiver or improve receiving noise figure. For commercial AM broadcast band receiver, a 10 dB or more signal to noise ratio of power at the output of the audio section is considered to be usable. Okay, let's continue with the tutorial for chapter 3, AM modulation and demodulation. So let's look for this first question. So a message signal of frequency 20 kHz and a peak value 10 volt is used to modulate at the carrier of frequency 2 MHz and peak voltage of 15 volt. Calculate modulation index. So in this question, it asks you to find the modulation index, which is m equal to, which is smaller m, sorry, equal to voltage modulating voltage over carrier voltage. So this is the equation if you want to find the modulation index. So in this question, they already give you the peak value of modulating signal and carrier signal. So here we can identify it. So Vm is the 10 volt and divide by Vc is 15 volt. So for this question, the answer is 10 divided by 15, you can get 0.67 for the modulation index. So if you want to find the percentage of modulation, which is the larger m, so you should get, you can use this equation, 0.67 times 100%. So you'll get 67% of modulation. Okay, simple question. Let's look for the second question. What is the carrier frequency in an AM wave when its highest frequency component is 850 Hz and the bandwidth of the signal is 50 Hz? So for this question, they give you the highest frequency, which is at 850 Hz, and the bandwidth of 50 Hz. So let's write it up here. So upper frequency, which is the higher frequency component, is the 850 Hz, and they also give you the bandwidth, which is 50 Hz. So you need to find the carrier frequency. So first you find the lower frequency first. So the lower frequency should be 850 minus 50 Hz. So you will get 800 Hertz. So let's draw the spectrum. Make it thicker. Okay, and then insert. This should be the carrier frequency. And we have the upper frequency and the lower frequency. So the upper frequency is 850. The low frequency is 800. So we know that at this middle here should be 850 minus 800 divided by 2. So you get 825 Hertz. So basically, so the middle here is the carrier frequency. So the carrier frequency will be FC will be 825 Hertz. So this is it's using a simple math. So the bandwidth here is 50 Hertz. With the upper side bandwidth is 25 Hertz. So you can just deduct the value and you'll get 825 Hertz for the carrier frequency. Okay, let's look into the next question. A modulating signal mt equal to 10 cos 2 pi times 10t is amplitude modulated with a carrier signal ct equal to 50 cos 2 pi times 15t. Find the modulation index, the carrier power, and the power required for transmitting the AM wave. So this is a AM transmitter. So how to find the modulation index first? So let's look into the equation. So for mt here is equal to 10 cos 2 pi times 10t, means that if you look at the equation, the general equation should be like this: mt equal to Vm cos 2 pi Fmt. So Vm is the voltage of the modulating signal. Fm is the frequency of the modulating signal. So from here we know that we can find Vm. And for general equation for the carrier signal is Vc cos 2 pi Fc. So for modulating index, M should be equal to Vm over Vc. So you get 10 divided by 50 and you will get modulation index of 0.2. How about the carrier power? So the carrier power PC, you need to use this equation. PC is equal to VC square, so I need to make it square here, divided by 2R. So this is the equation for the carrier power, VC square over 2R. So VC, they already gave it, which is this 50 volt, and R we can assume, so in this case we just assume R equal to 1 ohm. So with this we know that PC is equal to VC 50 square divided by 2 times 1 ohm. So you will get 1250 watt. Okay. So the next question is to find, let's delete this first because we don't have any space. Find the power required for transmitting AM wave. So to find the power required, we can use this equation. PT is equal to PC times 1 plus M square divided by 2. Okay, this should be like this. Okay, so it's easier to understand. So let's put all the value inside the equation. PC, we get it, we already calculated, 1250. 1 plus M is 0.2 that we already calculated, 0.2 square divided by 2. So here if you calculate it, you can get the answer is 1275 watt. Okay. Okay, for the last question, the equation of amplitude wave is given by ST equal to 20 1 plus 0 cos 2 pi 10 power of 3 t times cos 4 pi times 10 power of 5 t. So find the modulation index, carrier power, and the bandwidth of the AM wave. So this is the amplitude modulated wave equation. Equation, yes. So let's compare with the general equation of the amplitude modulated wave. So for the general equation is like this: ST is equal to VC times 1 plus M. M is the modulating modulation index, cos 2 pi. Let's copy it here. Times F M or FC FMT. So FM is modulating signal, cos 4 pi So not 4 pi, it's 2 pi times FCT. So this is the general equation for the amplitude modulated wave. So if you compare this equation to this equation, there's a small difference at this number only. So this is 4 pi and this is 2 pi. So you have to modify this equation to make it for you to easier to understand. So this should be 2 pi. So you need to add 2 times 10 power of 5t. So this is similar. Okay, we already have similar equation. Sorry, this is the wrong place we put. Okay, so now we can get the modulation index first. So m should be equal to this here, 0.8 modulation index. And then for carrier power, you can use the equation that I already discussed for the tutorial before, which is carrier power PC equal to VC squared over 2R, where we assume R is equal to 1 ohm. So PC here, you can write down here, VC should be 20, VC 20, R is 1. So you will get the answer is 200 watt. And lastly is the bandwidth. So bandwidth is, you can use this equation, 2 times 2fm, 2 times of the frequency of the modulated signal. So from here, 2 times, so where is fm? So you just compare this general equation to the equation given. So fm is here. So the value is 10 power of 3. Hertz. Sorry. Or we can say it is 2 kilohertz. So that's all for this chapter tutorial. Hope you understand. Okay, see you next week on chapter 4. Assalamualaikum warahmatullahi wabarakatuh.